Welcome to our online lecture series Radar in Action. As every Tuesday, we are broadcasting live from Wachtberg in the beautiful Rhineland in the west of Germany. My name is Jens Fiege, and I'm delighted that so many from all over the world are joining us again today. To be precise, more than 150 participants are online right now. What is it about today? Artificial intelligence and neural networks are trend topics that run through numerous areas, from mobility through production processes to defense. After all, the volumes of data collected are becoming increasingly larger, so steadily more support is needed to evaluate them. Although neural networks usually deliver good results, but it is usually not known how they arrive at these results. They resemble a black box. Do the neural networks do what they are supposed to do? Are their results reliable? These are the questions my colleague Simon Wagner is researching under the term explainable AI. He would like to present his current research results to you today. Please, Simon, go ahead.
Yeah, thank you very much, Jens, and thank you for these nice words. Welcome everybody to my presentation on machine learning for radar application. My name is Simon Wagner. I'm from the Cognitive Radar Department here at FHR. And today I want to show you some of our latest results on two topics, actually. The first one is small target detection, where we used a so-called contractive autoencoder. I will give you some more details on this in a few minutes, or on the next slide, actually, already. And then we will talk about target classification using convolutional neural networks. But I don't want to show you another example of how good these networks are. I want to focus on two topics actually that are related to robustness of classification. The first one is the so-called fooling problem, where we try to trick these networks to give a false classification, and we're looking for a way to avoid this situation. Another one is that Jens already mentioned, explainable AI. We want to have a look at the classification task and see what the network is actually using for classification of the input data. Okay, now we can start already with the first part, that's the small target detection with contractive autoencoders. I don't want to go too much into details about autoencoders. It's a kind of neural network that possesses or has two layers in the end, at least, an encoder layer and a decoder layer. That's what's depicted here. And a code layer in the middle, that's here. And actually, the main part of the autoencoder is about creating this code. This code should contain all information about the input data. And the decoder should be able to reconstruct the network out of this code. That's the basic structure, and actually we use undercomplete autoencoders. So the code has a lower dimension than the input signal. That means that we have a data compression in the autoencoder included. So we have, actually in our case, we use about 75% of the input size for the code layer. So we have a data compression, and we use a so-called contractive autoencoder. And don't be afraid, it's only one of two slides with formulas here. This actually includes a second term. So we have our data fidelity term where we try the reconstruction. So we want to reconstruct the input signal at the output. So that's the basic idea of an autoencoder. But we try to create a network that is robust against changes in the input data. And therefore, we include a second term here. That's the Jacobian matrix, or the Frobenius norm of the Jacobian matrix, that we can, written down here. And this is used to create an invariance against changes in the input data. So we don't want to have that the code changes with noise, or maybe also with clutter variations. For example, today it's very windy here in Wachtberg. And if we have a surveillance systems, we don't want to create false alarms all the time if we have a tree standing there and then we have some wind, and then it creates some false alarms. And therefore we use this here in a detection scheme, actually a change detection scheme. I want to show you just the basics of this, structure. First, we apply a radar system, and actually I will show you results from the SSRS system that was presented here 2 weeks ago. First, we measure only the background without any targets. And then we use a mean value of this background and initialize the bias term of the decoder with it. And this bias is then frozen during training. This is already some kind of hint actually to the network that we want to use here. And then we apply the training to the, or we run the training of the network where we use the background data, but also create artificial training data by using the background data and copy real targets into it at random position with random amplitude, and also just put a single pixel, for example, to a high value. And then for testing or for detection, we remove the bias during in the encoder that was frozen during the training. So it was all the time the mean value of the background. And then we reconstruct our test profiles. And since we have the mean background already in the bias term, we should only see variations from this background. And since we use the contractive autoencoder, we should also see only where we have really significant changes in the input data or in the test data. This is comparable, of course, to a background subtraction of a mean background subtraction. This is also used here as a reference method to show the benefit of this method. And what I want to give as a motivation is, of course, that it is comparable to background subtraction, but the data is processed by the autoencoder, by the neural network. So we hopefully have learned the statistic of the data, and then we can give a reliable classification or a detection. And I want to show you some examples actually of this. But before we look into the detection, I will just show you a comparison of the autoencoder reconstruction and a mean background subtraction for one certain example here. That's a part of the test data that we'll use later. We see here some ground reflections. There's this high wave here, more or less. And then we have here two peaks. One belongs to the background, and the larger one is actually a target. And this large value we can see in both outputs. We can see it in the autoencoder output, but also in the mean background subtraction output. The main difference is that we actually have, because of this high variations here close to the radar. So the radar is placed here. And then we have stronger echo returns near the radar, of course. It was something like 100 meters or something was the measurement range here. Or maybe 200, actually, I don't know. And the difference is now that when we have already weak radar returns quite far away from the radar, we can see that the mean background subtraction has less, I call it noise floor here. It's not really noise, but it's the variation of the background here compared to the autoencoder. But close to the radar, where we have these high peaks, the autoencoder actually has much lower values than the mean background subtraction. And this should give us less false alarms, actually, because we have less amplitudes in our lower amplitudes in our reconstruction at positions where we don't have a target. And actually closer to the radar, it actually gets worse. And I want to show you some examples. The first one is a detection of a person standing on the ground. And I actually marked the person here with these red lines. You can see them here. Sometimes it's really hard to see the person. Sometimes it's a bit stronger than the peak that we just saw, and sometimes it's comparable. And now I want to show you the detection results in terms of these RROC curves that are often used in radar detection. And I actually did it also in this logarithmic scale here on this side. And you can already see that the first false alarm for the autoencoder part happens after more than 50% of the real targets were already detected. So in this case, we knew where the target is. We had a certain amount of test data where the targets did not move. And then, we were able to detect this person in 50% of the range profiles before we have the first false alarm. But over the whole range of this low false alarm rates, we have a much higher detection rate with the autoencoder than with the mean background subtraction. Because we have this many false alarms, actually most of them here very close to the radar where we have this very high peak. If you have very high false alarm rates, it's a bit hard to see actually in these slides in the graph, but in this case, the mean background subtraction gets better, a bit better than the autoencoder, and the reason is that we have this noise floor that I showed you just on the last slide. In this case, we have with this very low threshold values, a higher rate of false alarms for the autoencoder because of this more or less, let's say, constant noise floor on this slide. And I will also show you an example with 2 drones, where we measured 2 drones hovering over each other at the same position, so they did not move again. So we knew where the target is. It's also here, so it's also again quite hard to see sometimes comparable to the background. And in this case, it's not as evident as in the case with the person, but it's still that we have the first false alarm after we have already 30% of the detections. I would say that's quite good. And it's also again here that we have, because of this noise floor, a lower detection rate for very high false alarms rates. But in the more relevant part of the low false alarm rates, we have much better detection rate. And of course, something I can't show you today because so far I didn't do it, but a possible outlook would be, of course, a combination of both. That we do an analysis where we have how much variation in the background, and then we can combine the autoencoder in areas with high variations and the mean background subtraction in quite stable areas. So that was already the part with the autoencoder, so the target detection. Now we come to the second part, the classification part. And in this case, I want to use convolutional neural networks, which give state-of-the-art results for all kind of classification tasks. But as Jens already mentioned, it's kind of a black box behavior. So we don't know exactly what they are doing. And another open point is actually robustness. And I showed you here an example with micro-Doppler data actually. So we see a spectrogram of a walking person. And we want to classify actually if the person is walking or not. This was one example of applications, but today I want to focus actually on classification of SAR images. Just to show you the variety of applications where these networks can be applied. It can be really mainly to imaging radars, because a lot of this comes from computer vision, but also to micro-Doppler, or also there are also publications using it for surveillance radar also. Okay, so today we want to have the robustness of these networks, and the first one is the so-called fooling problem. The fooling problem is well known in the optical domain. It refers to the intentional manipulation of the input data to create a false result of the neural network. I will show you an example, because I should mention that very often it's really a small amount of noise that is enough to trick these networks. And this is almost invisible for us as a human observer. This example here, you can see, I hope you can see a cat. But if we trust the very deep neural network that students from MIT used for classification, it's guacamole. This is, of course, wrong. So in this case, it was quite easy to trick this network. It was a very deep network, and it was in some way looking for the wrong features here. I don't know the reason, but it sees guacamole in this picture of a cat. Another example where the content did not change is this stop sign. So we have, it's of course also in the optical domain. So we have a classification system for traffic signs. And this was able to classify regular stop signs more or less perfectly. And then they put some black and white stickers on this stop sign. And then somehow the network classifies it as a 45 miles per hour speed limit. This is, of course, if you think about autonomous driving, for example, quite important that we have a robust classification and that we see a stop sign as a stop sign and not as something else, also in challenging situations. And that's one of the reasons why we want to harden the network against fooling, because in this case we also have intrinsic invariance against target variations. If you think about radar targets, it might be, for example, if you want to classify cars, for example, a car with an open door is still the same car, but it might look different and we might get a wrong result. And in this, for this first investigation, we used something called DeepFool. That's an algorithm that was published a couple of years ago. And we use it here for SAR images, for the classification of SAR images. And it's a so-called white box attack. That's something that's in sort of really attacking an algorithm, not that realistic. But as I said, it's a very first investigation. And yeah, it's in quite, especially because the algorithm is very easy to implement. We use this, and yeah, it was quite also possible with this to create the fooling examples and to harden the network. I will show you the basic idea of this network with this slide. So this is the second slide with formulas here. If you think of a simple binary classifier, like a linear support vector machine here in two-dimensional input space, we have a certain example, x0, that is classified correctly now. We have some result here, f of x is larger than 0, we are on the correct side, so we have a correct classification. And now, in this case, we can project actually this point on this line here, on our classifier line, and then we just add a little bit more, and then we push it on the other side, and then we have a wrong classification. That's the basic idea of this network, just as in case of neural networks of this algorithm. Just in case of neural networks, we don't have this simple hyperplanes as, or linear hyperplanes as separation parts between the different classes. It's quite high dimensional and it's not linear. So we have this is actually a greedy approach, but we can, it finds quite good solutions for arbitrary LP norms between 1 and infinity. And I will show you examples for 3 different norms: L1, a sparse perturbation, L2, and the infinity norm, so the maximum norm. And this was done, it was done quite easily because the authors of the original papers give implementation in MATLAB and in Python for this algorithm. And I want to show you something, I already mentioned it in L1, L2, and the maximum metric. And we used for this, to create these examples, a standard CNN, let's say standard, with a normal softmax output layer, without any provisions against fooling. And this is actually what happens. So we see here the original image that was classified correctly. Here you can see the L1 perturbation. It creates a sparse perturbation, really. You can see that just a few pixels are changed to a very high value. In case of the L2 and the L infinity metric, it's really that we have, it's really like noise that is added to the image. It's still, it looks like the original image, but you can see that there's some more also in the background, but also on the target area. The shadow area has changed a bit. I hope you can see it on the slides. There you can see it. It's more like noise, and the maximum metric actually changes. It's like a constant offset almost. It's not constant, it's changed a bit over the image. Like the right half is going up by a certain amount and the left part of the image is going down a bit by a certain amount, but that's what happened, what's enough to fool the network, let's say, to give us a wrong classification. And then we tried some methods to avoid this fooling. And the one that we used in the end is called competitive overcomplete output layer, which is abbreviated by the acronym COOL. It was introduced in 2017. And the idea is that we don't have one neuron per output class, as we have in a standard softmax normally. We collect neurons in so-called aggregates. So we have for each class a certain number of neurons. Actually, this number is defined here as omega. And we have a competition in this network, in this output layer, because the whole output layer is implemented as softmax. So we have this competition. I will show you a quick example with with omega is equal to 2. You can see the standard network here. This is the standard softmax, where we have one neuron per output class. And we have, for example, if we have an image of class number 2, we want to reach this desired output. We want all zeros except the second output is 1. So it's one of these so-called one-hot vectors. If we now use this cool output layer, we have 2 neurons per output class. If we have with omega is 2. And then everything we have to change is actually that we need to change the desired output. We just changed this values of 1 to 1 over omega, in this case 0.5. All others from the other aggregates are 0. So this is, in the end, everything we have to change. We can still use the same training methods, everything. We just increase the number of output neurons and change the desired output. The classification afterwards is done. We apply the network to the test data, and then we get some results, some numbers here in the output layer. And if you think of exactly these numbers here, and then multiply them again by omega, in this case 2, we have there 0, 0, 1, 1, more zeros. We multiply these and by 2 and multiply the aggregates together, and then we have again 0, 1, 0, the one that we reach there at the top. So this is everything we want to reach in the end. And this is a very simple way to create these, not simple way, but in the end it is simple, but it's a very good way to have 2 benefits actually. We have at one point this hardening against fooling, which I will show you on the next slide. But also we have a higher variation of the output rates. So if we want to give some sort of how certain is the network about the result, we normally give the number of the softmax output. And maybe some of you know that these numbers are normally quite high. And with this we get a higher variation and might have a better, for example, rejection rate or something like this. Okay, I will show you some examples. We take the network, we take 100 random samples out of our test data, and we put the number of maximum or number of iterations to maximum 10,000 for this network. And then we simply count for how many images we could create this fooling results. And then we see that if we use the standard softmax output, we have in L1 metric 61 samples, in L2 90, in maximum metric 93. And then we can reduce this about to 1/3 or to 50% if we use this cool output. So I would say this is quite a success in terms of robustness. And so far we also that's the result with the cool. And actually next week on the radar conference, you will see some more of this with other methods. So this was kind of a sneak preview, let's say, for the presentation next week. And now I want to go on with the explainable AI part. And there it's quite important that to show that we actually use the target area of these R images for classification. Because it was shown in the past that the Amster dataset that is used quite often for classification, it is possible to simply classify the data by using only the clutter area of the images. And here we want to use these tools of explainable AI to show that our networks are focusing on the target area, not the clutter area. And we do this by generating heat maps, actually, that I will show you next, where we see where the target or where the network is focusing on in the input image. And this is supposed to be a first look into the black box behavior. So here are some examples. You can see here the original image. There you can see the heat map and the overlay. And there you can see that the center of this one is really on the target area, especially very often on the transition between shadow and target. This was just to show you some examples. And if we now do this for the whole data set, and then we calculate the center of mass for all of these images, of the heat maps for all targets, for all images, and then we can project it, or not project it, we simply plot it here on the input images, and then we see the center of mass here as this red dot. and this ellipse around is the 5 sigma boundary around this. So this is the, let's say, proof that our network was focusing on the target area, not on the clutter area. Okay, that was already my presentation, more or less. I want to give you a short summary and a conclusion. So we've shown that the autoencoder reconstruction is beneficial in areas where we have large clutter variations for detection, and that we still have better results with the mean background subtraction in the areas of stable clutter. So it might be possible to combine these in the future to have the benefits of both. The second part was the classification with convolutional neural networks. So we have the increased robustness against fooling. I think I didn't mention it actually just before, but it comes, of course, with a price. So we have an increased training time, and we also have a slightly reduced correct classification rate for the known targets. So we have an increased robustness, but for the known targets, we have a slightly reduced classification rate. So for the explainable AI part, it is of course good to know that our networks are focusing on the target area, not on the clutter. But it is of course only a first look into the black box. Now we know where the target or the network is focusing on, but we still need to explain the behavior, how this feature extraction works, how the classification works. So this is of course part for our future work. And I want to show you, just some upcoming presentations or some papers. So the results presented here are so far not published, but will be published hopefully in the next weeks, in months or something. And I think the UROT, where we submitted the explainable AI part, is shifted now to next year. But I think there's a paper coming up then next year. Thank you very much. And I think now it's time for questions. So Jens, I think it's up to you.
Thank you, Simon, for your really very challenging talk. I hope you experts could follow him. There are some questions, so I will go ahead. Is RROC an appropriate metric? I assume that the data set is highly imbalanced in the radar signature or images comparatively very low number of targets compared to clutter.
I would still, it is appropriate because it's the standard way to give detection results, more or less. It is, of course, imbalanced because we have only a single target over the whole range of the range profiles, more or less. But in the end, I would say it's the only way to give really a detection result. If you have the RROC curve, if you want to know, how many classifications did we reach for a certain false alarm rate, I would say it's the only way actually to give these results. But if you have better ideas, I'm open for this. You might contact me and send me an email.
Okay, great. Here's the next question from the same person. It's very long. Autoencoder was trained on first, background only, clutter radius image signatures, no targets. Second, artificial target data, radar images with background and some pixels set to high to simulate targets. Isn't this an idealistic modeling of target radar signatures? A cluster of high pixels surrounded by signatures of background clutter was an EM or microwave modeling and simulation software not used to generate simulated target signatures in a given environment. Did you get this?
Yeah, I think so. Thank you very much for this question, actually. I would say because this was designed for a surveillance radar. So we have a given scenario and we have a given background. So the idea actually in this scenario is that we place a radar somewhere and then we perform a measurement of the background and then we train the network more or less in field for detection. That's the idea so far. So that was the reason why we have this we only use the measured background where we use the measured background data but we also, the targets that we placed in these profiles were also measured by the same radar. So we have independently measured targets placed on this, on these profiles. And then we, I would say that's some of the best test data that you can guess, because you have the real background with real targets measured by the same radar. And this is something you can't reach with simulations, I would say. Of course, if you want to have higher variations, also for the targets that you might expect, modeling might be an option. But in this case, I would say it's quite a good choice to use these examples, I would say, to use the measured data from the radar that we have in our database.
Okay, next question. On what basis the number of neurons are changed?
In the end, simply trial and error. There's so far, for me at least, I don't know a really certain way to really define the number of neurons for a given network. Actually, for the cruel network, we didn't use omega as 2, we use it as 10. So we have 10 output neurons per class. That was also a reason why we have this increased training time. So we have really increased the size a lot. But yeah, it was quite good to have so many neurons classifying the same target, because then we get quite stable, or let's say stable classification results with an increased robustness. But in the end, the number of neurons is simply so far just by trial and error a bit. After some time, you get, of course, a feeling how many neurons you need, but so far it's only done by trial and error.
Okay, thank you. Is it a brute force method you use for the selecting the number of nodes and pooling layers, or by optimization? The same, maybe it's part of the question before.
Yes, it's. I would say it's more or less the same question, but it's it's not really optimizing. As I said, after some time, you get some sort of feeling, I would say. Actually, the networks that I use are a bit different from the one that you see in computer vision, where they use very small features, simply 3x3 or 5x5 filters. I normally use larger filters, actually. For me, it was, for example, quite good to use filters with a size of about 20% of the input image. So that's a bit of a difference, but this comes by experience, not really by optimizing, if that's okay as an answer.
Okay, next question. If the data for target classification is always RD heat maps, have you tried before spectrograms or scalograms, wavelet as data?
So we didn't use the heat map for classification. We used the SAR image, and then we calculated the heat map. But we also used spectrograms, but not for, of course, not in SAR images. We used it, for example, I showed the network I showed was for classification of walking people. So for classification of movement, there we used spectrograms. So we do time frequency transformation and look into these features. But here I was focusing on SAR images, so an imaging radar.
Great. There are many questions. The data used to evaluate drones detection with CNNS is made of microdoppler spectrograms.
The detection is simple based on high resolution range profiles and also a real valued one. So we have only a single snapshot. So we don't have really a series of measurements. We have a scanning surveillance radar. So we always have for, I don't know the update rate now. I think it was about 2 updates per second or something. And we have always just a single snapshot of a certain direction. And we only use this single snapshot for the detection of the drones. So in this case, it was no microdoppler, so we don't use movement here. We simply use really the, let's say, RCS, so only the fluctuation compared to the background data. So it's not like an MTI method where we have some moving targets. It's really just based on plain detection in the RCS data.
Thank you. Here's a note for you. Can you write this conference to your LinkedIn profiles from a student? Yeah, maybe you can do this, Simon. We will check this. Next question. What is the most efficient model to train microdoppler signatures? Similar to the question before?
Yeah, so far, my experience is more that I don't use these pre-trained networks. I see in the question that they also mentioned about ResNet or something, but I create normally my own very small networks because the data that we classify, in some way it's quite scarce data, so it's not that many. And we normally have quite small, let's say small problems. So if we want to, for example, classify rotary drones or fixed wing drones, for example, it's mainly 2 classes, 3 classes, maybe 5 classes, but many of these networks that you find are trained for 1,000 classes, for example. And this is simply something we don't need in the end. So I normally prefer to create my own smaller networks, but use the structures of the larger ones. So use the convolutional filters, the pooling layers and everything. So the structure of the networks, but create my own smaller network. That's at least what I'm doing so far.
Okay, and next question. What would be an appropriate way to model an interferer into the fooling approach?
That's a really good question, I would say. So far, I don't have an answer to this, because in this case, you should, some sort of give a hint to the fooling algorithm already. So it's you have to know the structure, maybe of how the interferer is working, I would say, how the jammer is working. And then you know what you are looking for, and then you can use maybe the fooling algorithm somehow to harden your network also against some certain type of attack, let's say. But so far I didn't do something like this, but it's quite interesting, and this might be something to think about in the future, really. So far I can't really give an answer to this one, but I will think about it, let's say.
Oh, great. Yeah, some work to do. We have very, very many questions, so we are very sorry that we couldn't answer every question. If your question was not answered, please write an email to Simon or to me, and we will answer it via email. Here are 1 or 2 we can answer. What does the background consist in? For example, sea land clutter.
This was mainly now grassland, and also I think there was also a road, so it was land clutter. So it was actually measured here on our facilities. I think it was mainly, there was maybe also a tree in there, and at some point they placed a corner, so some, like a strong target, but it was mainly a road and also grassland, I would say.
Yeah, okay, and here comes the last question for today. What is the input data to the network? To be precise, what exactly is the radar measuring? Is it just distance to targets or also the range rate? Do you do any pre-processing before feeding the data to the network? Have you tried using a time series of data rather than a single frame? Also, do you use the range data only or also the Doppler?
I don't know to which network the question is related, but for the autoencoder, for example, it's only range profile. So we use RCS over range. Or I think it was not calibrated, so not really RCS, but the relative comparison between target and background data. We also used Doppler data, of course, but this was this was more for the classification of movements, walking or cyclists, for example. And the detection was also done on single frames, so there was no time series or something. It was just a single frame detection. So this can, of course, also be improved by if you use, for example, a coherent integration over time. So you can, of course, improve these results further, but it was designed for this scenario that we have this surveillance radar, that we have a fixed update rate and want to give let's say give a detection after each rotation of the radar. So in the end, we use many kinds of data, but here it was for the autoencoder single HRR profiles, and for the convolutional networks, it was SAR images. So it used, of course, the different observation angles, but it was also no time series or Doppler data in there.
So now we are at the end. Thank you all for today. Thank you again for your participation and all the questions. I hope you enjoyed it. Again, you will get a short survey tomorrow. We would appreciate it if you would take the 2 minutes to answer the 4 questions. And on Friday, you will also receive the presentation slides from today. And in case you didn't know, in about 3 weeks, the presentation will be published on our YouTube channel. It's the best to subscribe to our channel Fraunhofer FHR, then you won't miss anything. Because this Thursday, the next session will be published there. Finally, let's take a look at the next lectures. Next week, there will be another special talk. We will broadcast live from our Space Observation Radar Tyra with my colleague Nora Egli, but in German. The next English talk will take place in 2 weeks. It will be about DVB-S-based passive radar imaging. More information can be found on our website. Google for radar in action, you will find it. So if you haven't registered yet, do it now. See you next week or in 2 weeks. Take care and stay healthy. Goodbye.